Okay, this video is going to cover electron configurations with all sort of parts included. Regular electron configuration, orbital diagrams, electron configuration of ions, noble gas notation, and electron configuration of excited state electrons. So I'm going to start by going over what the orbitals actually look like that these electrons fill in. Now remember, it was Bohr, Thomson was the first one to discover the electron through his cathode ray tube experiments. He just kind of proposed that they were mixed into the atom like plum pudding. Bohr had the idea, of course Rutherford discovered the nucleus. Bohr figured the electrons were in these concentric circles like this. And it wasn't until Schrödinger and Heisenberg that we figured out the true shapes, or at least as true as we believe them to be now, the true shapes of where the electrons actually are. So the first two electrons, let me imagine my nucleus here. The first two electrons fill in the 1s orbital. The S stands for sharp, P stands for principal, and so on. These terms kind of have to do with optics, a study of light, but I like to think that S refers to sphere, because that's basically what it looks like. So the S orbital is just a sphere that surrounds the nucleus, and there are two electrons inside that sphere. The second two, or I should say the next two electrons will fill in the 2s, like this. Now it looks like I'm drawing the Bohr model here, but I'm not. I'm not trying to show the electrons as stuck on the outside rings. They're flowing throughout those two spheres. The next 6 electrons are located in 3 p orbitals. So I do these in a different color. 2p, because we're still at level 2. And the p orbitals look like this. They're sort of like bow ties with these lobes, where that is one orbital. There are 2 electrons that follow this sort of bow tie shape. They can kind of teleport from one side to the other. 2 more are in this p orbital. And we generally call these 2px, 2py, and the third one's going to be 2pz, which is 3-dimensional. Z is like the z-plane in math. It's coming straight out towards you and straight into the board. And a lot of times you represent that as like a dashed line going like this. Okay? So this represents the first 10 electrons. 2 of them are in here, 2 of them are in here, and 6 of them are in here. And remember, every orbital can only ever hold 2 electrons, so the 2p is made up of 3 separate orbitals. After that comes the 3s, which is another sphere. So there are 2 more electrons that are within this outer sphere. After 3s is 3p, which holds 6 electrons. So the 3p is made up of 3 separate p orbitals. And it looks something like this, where it's the same shapes, but they're a little bit larger. And note that these p orbitals are within the bounds of the previous s. That's important when we talk about trends like atomic radius. Okay. After this comes 4s, that can hold 2 electrons, so that's another outer sphere. Here's your 4s, 2 electrons in there. And then after 4s, we jump into the range of d orbitals. Now in Chem 1-2, we're not going to be covering the shapes of those d orbitals. I pulled up a picture here. There are 10 electrons that fill in each layer of the d orbitals. So these are the 5 d orbitals that could represent something like 3d10 or 4d10. We don't have to worry about these shapes in Chem 1-2, but you should understand the basic shapes of the s and the p orbitals. Now let's go over the actual order that they fill in once again. And instead of trying to memorize all this, you just kind of look at the periodic table. Okay. So we start at the very top, hydrogen. Now for the sake of this, I like to imagine helium is over here, because it makes it a little easier. All you really have to memorize is this. All of these first 2 columns, which we call groups, are associated with letter S. These groups are associated with the letter P. These groups are associated with letter D. Okay? So, if we have to fill in the first 2 electrons, again, imagine helium's right over here. We're going to say 1s1, 1s2, because they start filling in the level 1 s orbital, and they hold 2 electrons. So if you have helium here, it's going to have 2 electrons in the 1s orbital, so you write 1s2. The 2 is a superscript, looks like an exponent. The next 2 fill into the 2s, and the pattern sort of matches the periodic table. You go 1, 2, again, imagine helium's right here. After 2 is 3 and 4 right here. So that's your 2s. After this, you follow the numbers. Here's 5 through 10, that's your 2p6. Follow this, 3s2, 3p6, 4s2, and now we have these d orbitals. Okay? With d orbitals, one more thing you have to memorize is that we drop down one number when we talk about the d orbitals. And that's true because within the atom, the d level actually is lower than the s and the p. It just fills after those s and p. Anyway, this is going to start as 4s2, and it's going to drop down and become 3d10. Then, when you're done with that, you jump right back up, and we have 4p6. 5s2, drop down a number, 4d10. After that, we jump right back up, 5p6, 6s2. Now, there are orbitals beyond this called f orbitals, but we're not going to cover those in Chem 1-2. So these are all that you need to know is 1 through 56. All right, so let's practice writing some electron configurations out. All right, imagine we want to write configuration for carbon. We look at the periodic table, which you should have with you, and you see the first two are going to fill in 1s, so we just write 1s2. The next two are going to fill in the 2s, and then we look at how many we have left, and it's going to be 2. Okay, so we just write 2p2. You don't write 2p6 unless all 6 of them are occupied. Let's do another example, calcium. So if we look over at calcium, you can see it's going to end right around here, number 20. So we're going to write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And again, you don't have to memorize this entire sequence. You just follow the periodic table and remember which letter is associated with which groups. All right, let's do one more. I'm going to pick something involving d orbitals. Let's do yttrium, element number 39, yttrium. So let's look at where yttrium is. Right here. And I could tell that we're going to complete the first 4 numbers. We're going to drop down and do 5s2, and then we have one more. So let's look at how we fill these in. It's going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That covers the first 20. And now is when we have to pause and think about our d orbitals. So when we do the d orbitals, we drop down a number. So I'm going to say 3d, and since it's going to fill the entire row, we say 3d10. If we go beyond that, we're going to jump back up, and we say 4p6. And now we're at rubidium 37, so we say 5s2. And now if you look over here, we have just one left, one electron left to fill. Because here's your 5s2, and here's yttrium. So we just end this with 4d1. Just like that. Okay. Let's talk about orbital diagrams. In orbital diagrams, we're going to use up and down arrows to represent the spin of electrons. Electrons basically spin either top spin or bottom spin. And if there are 2 electrons occupying the same specific orbital, they have to have opposite spins. So let's come up with an example here. Let's do magnesium. Okay. So you should know how to do the electron configuration of magnesium. Basically, it's going to be 1s2, 2s2, 2p6, 3s2. Now we're going to represent that by showing the actual electrons. And what you do is you put one s and a line, and we need to show one up and one down with an up and a down arrow. Now, for the sake of time, you don't have to really do the full arrow like this because it could take you a long time. So what we usually do is just shorten it like that. One up and one down. Okay, after that we have 2s, and that's definitely going to be filled. And now the 2p. Now remember, the 2p is not one orbital. It's 3 orbitals, each of which holds 2. So 3 times 2 is 2p6. So what you do is you make all 3 lines and you put 2p. All right. Now the way you want to fill these is in a certain order. They always have to be put in separate orbitals first until you have to pair them up. The metaphor we use is like if you have 2 brothers and sisters and you 3 all hate one another and your parents say, well, you can each have your own rooms or you can double up. You're obviously going to each choose your own rooms first until you have to. You know, if you then have 3 more kids, they're going to have to double up those rooms. So the first 3 are going to fill in like this, and then as 4, 5, and 6 come, you have to pair them up. Okay? And again, thinking about the atom, the reason that these are going to fill separate orbitals first is because electrons are all negatively charged, so they all repel one another. So if you give 3 electrons a choice of which orbital they want to occupy, they're always going to spread as far apart as they can until you force them to come together. After that, we just have 1 orbital left, 3s, and since this is 3s2, we just end with up and down. So that's it for magnesium. Let's do another example here. I'm going to choose, let's see, molybdenum. Element number 42, molybdenum. So, looking at where this is going to end, it's always good to see sort of your game plan first. I can see it's going to end with 5s2 and then 4d4. Just thinking that ahead. All right. Molybdenum, MO. So we start with 1s2, 2s2, 2p gets 3 lines, up, 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 down, 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 3s2, 3p. Now look, if you know they're going to be filled, you don't have to go up, 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 down, down, down. You can just go up, down, up, down, up, down. But it's a good practice. Up, up, down, down, down. 4s is going to be filled, and now it's the first level of D. So 10 electrons make up the D. So we're going to make that 5 separate orbitals, because remember, that's what they look like. It's 5 orbitals. So we drop down a number and say 3D with 1, 2, 3, 4, 5 lines. 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, after 3D comes 4P. 1, 2, 3. 5s, up and down, and now I'm going to slow down and be careful here, make sure I don't sort of overshoot what I want. Here's my 5s2, and here's molybdenum. So I need 1, 2, 3, 4 more electrons. But even though I only need 4 electrons, so I'm really only going to need 4 orbitals, I want to draw all 5 of my lines, just to show that in theory you could put more electrons in there. Now this is going to be 4D, remember you drop 1 number down, and we go 1, 2, 3, 4. Like that. Okay. Let's move on. We're going to talk about, where is it? Electron configuration of ions. Okay, so this is pretty straightforward. Let's start with a cation and then we'll do an anion. Let's do strontium first. Strontium. So the difference between an atom and an ion is that one has a charge and one doesn't. But what that really means is to make an ion, you have to adjust the number of electrons. You can't add or subtract protons to turn it into a plus or minus charge, because if you adjust the number of protons, you change the element you're looking at. So we're going to be adjusting the number of electrons. So if I want to do a strontium ion, you should know from writing formulas that this is going to be a strontium 2+. All right, but let's just start by writing what strontium is just by itself. So take a look at where strontium is going to end up, 5s2. And write the configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, down to 3d10, up to 4p6, and now 5s2. Okay? So that's strontium. But if I want to make a strontium ion, I'm going to have to adjust the number of electrons. So since strontium forms a 2+, that means I need to remove 2 electrons. You're going to take away negative charges to give it that positive charge. Now the question is, which 2 do we remove? And in this case, it's very simple and straightforward. You're going to remove the last ones. But it's not always going to be the last ones you write out. It's always going to be the ones with the highest energy level. Now, this number here is called a principal quantum number, and you could think of it representing something like distance from the nucleus. You know, as we mentioned with our shapes here, these s orbitals are like different spheres. So in this case, if I have another s orbital, those are going to be my two outermost electrons. Okay? So in this case, the two electrons that are easiest for strontium to lose are definitely going to be those 5s2. So all you do is erase this. And this is your ion configuration. And you'll notice, whenever you make an ion configuration, it should resemble a noble gases configuration. In this case, it looks like krypton, because it ends with 4s2, 3d10, 4p6. And if you look at the valence electrons, which are always your outermost energy level electrons, here's 4, here's 4. If you add it up, 2 and 6 is 8. That's what they always go for. Let's pick another one here. Let's do manganese, Mn. Okay. Now manganese is a transition metal, so I'm going to have to tell you what ion we're looking at here. Imagine we're looking at a manganese 2+. Okay. Remember, transition metals can form all different charges. So let me write my configuration for regular manganese and then we'll adjust it. Now, obviously, if you know what it's going to be, you don't have to write out the regular one and then adjust it. You can just write the correct one. Manganese ends, it's going to end with 3d4, 5, 3d5. So let me write that out. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. That's regular old manganese. So without the 2+. Now, if I want to turn this into manganese 2+, I need to remove 2 electrons. So the question is, where do I pull those 2 electrons from? And the answer is you're going to look at the highest energy level or different distance from the nucleus, which is represented by these coefficients. So even though we end with 3d5, the highest energy level is 4s2, and these are the 2 that we're going to remove. Okay? So we're going to remove these 2. And that's not going to work. You would just put it back together again. So it would end in 3p6, 3d5, like that. Okay. Let's do another example of an ion. This time let's do an anion. Imagine I have chlorine, and I want to make a chloride ion. So here's chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. That's regular old chlorine. If I want to make a chloride ion, which is going to end in which is going to be Cl-, I'm going to have to add an electron to this, add a negative charge. So where do I want to fit that in? It's obviously going to go right here. Make this a 3p6. And this just shows you why things like chlorine are so reactive. It's so close to filling up its valence electron shell here. It has 2 and 5. It has 7 and wants to get to 8. So that's why it's very, very reactive. So you would just make this a 6, and that becomes your Cl-. Noble gas notation. This is sort of a shortcut. Basically what you do is you, if I tell you I want to see like the noble gas notation of phosphorus, you're going to look at the previous noble gas, which is element in group number 18, far right. You put that in brackets, and then you add whatever is left over, whatever's extra. So let's do that example for phosphorus. So I look on my periodic table, find phosphorus, and I'm going to backtrack until I get to the last noble gas. Remember, these are noble gases, so the last one before phosphorus is going to be neon. So you put neon in brackets, and we write whatever's left, which in this case is 3s2, 3p3. Okay? And really what the bracket represents is the same configuration that neon has, plus this, plus that. Okay? And it works for all of them in the d orbitals as well. Let's choose something like iodine. Okay, we find iodine, element number 53. Previous noble gas is going to be krypton. So we put krypton in brackets. Krypton, and we are going to add to krypton 5s2, 4d10, 5p5. That's noble gas notation. It shows all the electrons that follow it. And just to be clear, this does not necessarily show the valence electrons. In this case, it does, because what's my outermost level? Well, it's level 3. I don't have anything in level 4 here. So you would say 2 and 3 gives me 5 valence electrons, and that's true. Phosphorus has 5. But in this case, if you want to say how many valence electrons in iodine, you don't say 2, 12, 17. It's not 17. The outermost level is energy level 5. So you would say 2 and 5, 7. Okay. Last thing I'm going to cover is ground state versus excited state. And for this, I'm going to go back to my Bohr model just as a representation, because Bohr model does a great job with this. I could do the same thing with the Schrodinger-Heisenberg model, but it's a little more complicated. It takes longer to draw. So imagine I have a helium atom. Helium is going to have 2 electrons in the 1s orbital, so 1s2. If these electrons happen to get hit with energy, with just the right amount of energy, just the right frequency, just the right angle, they can become what we call excited, where they jump up. So imagine this one gets hit by energy. This electron, let me do it with, this electron can jump to here. Or if it gets enough energy, it can jump to here. And again, this is simplified in the Bohr model. If you have an electron in the 1s orbital, it can jump up to the 2s. It can jump up to the 2p. It can jump up to the 3s, and so on. It depends on how much energy it gets hit with, tells us where it's going to basically end up. So right now, this is now a helium atom with an excited electron in one of its outer orbitals. Now, it can't stay up there forever. What will eventually happen is it's going to lose its energy and release it. Now, when that energy gets released, this is going to return down to where it started, which is called its ground state. So basically, electrons can jump up when they gain energy, then they release energy, and they drop back down to ground state. Now, the energy that it releases when it drops back down, that's what our eyes pick up as visible light, if it happens to have a certain wavelength. So anytime you see color, that you're basically seeing electrons jumping up and jumping down and releasing that energy. Okay? So let's talk about what the configuration of an excited electron could look like. Same example. Let's say I have helium. If I want to say helium, but this is the ground state, it would just be 1s2. That's it, 1s2. But if I want to say a helium with 1 electron in the excited state, we're going to leave 1 electron in the ground state, 1s1. And now that electron in the excited state can jump up to any one of the higher energy levels, so let's just put it as 2s1. So this is an example of helium with 1 excited state electron. You could also say 2p1, you could say 3d1, you could say pick basically any orbital you want. And if we drew these in orbital diagrams, you could see the same thing. For helium, ground state looks like this. But if you excite one of these electrons, now we're going to look like this. 1s, oh, wrong way on that. 1s1, 2s1. Or if I put this in something like 2p, it's still a good idea to put all of your orbitals in. You can go like this. So this is an acceptable orbital diagram only if you specifically mention that that electron is excited. It's in an excited state. Okay. So those are my descriptions of those topics. What I have is a sample set of problems right here. My suggestion, pause the video, take 10 minutes, try to work all these out, unpause it, and I'll go through them. Okay? So let me start now. Electron configuration of boron. Bromine. Bromine is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Just making sure I don't shoot past it. Where's bromine going to end up? Oh, I did. Bromine is going to end up as 4p5. Sodium. I can tell what it's going to end as, 3s1. So I'm going to say 1s2, 2s2, 2p6, 3s1. ZR, that's zirconium, number 40. So I can tell where that's going to end. It's going to end in that 4D region, and it's going to be 2N. So ZR, I'm going to say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Now let me slow down here. Oh, nope, 3d is totally completed. 4p6, 5s2, and now is where I need to slow down. 4d2. And again, I know it ends in 4d2 because here's my zirconium, and here's 5s2, so now it goes 4d1, 4d2. Second electron in there. All right, last couple here, calcium ion. So you need to know what ion calcium tends to form, which is always going to be a 2+. In fact, if you don't remember that, this is a good way to identify that. So here's calcium. I'm just going to do this one imagining I don't know what ion calcium forms. Well, here's calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So if I said, hey, this is a certain atom, certain element, and you want to make an ion out of it, well, you have two choices. You can either bring the number of valence electrons up to 8, or you can bring it down to 0. But of course, when you make it 0, you're really just making the previous shell the valence shell. So in this case, I have 2 electrons in my outermost shell, so it would be a lot easier for this one to lose 2. That's exactly what it does. Calcium is going to lose 2 valence electrons to form Ca2+. And now, it doesn't really have 0 valence electrons. Now it has 8. My other example is going to be oxygen ion. That's going to be O2-. So it's going to look like this. 1s2, 2s2, 2p6. Oxygen normally ends in 2p4, but I'm going to add 2 more electrons. All right, orbital diagrams. SB, that is antimony. Yes, number 51. All right, so I'm just going to look ahead to see where it's going to end. It looks like it's going to end in 5p, 5p3. So I'm going to do everything before then. 1s2, 2s2, 2p gets 3 lines. Here's your 2p6. Here's your 3s2. Here's your 3p6. I'm breaking my own rule here because I know they're all going to be filled. 4s2. Now we drop down to 3d10. We're going to do all 5 lines for 3d10. Okay, jump back up to 4p6. 5s2. Let me just make sure I'm not going too fast here. Yep, I'm okay. So 4d10 is going to be totally filled now. Up, 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 up. Down, 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 down. And here's where I got to be careful, because I know I'm going to end somewhere in 4p. 1, 2, 3 lines. And since I can see that I'm going to end 3 electrons in, I'm just going to go up, up, up. So that is your orbital diagram. Magnesium ion. That's going to be Mg2+, which is going to, magnesium would end as 3s2, but I could tell I'm going to pull those 2 electrons out. So I'm going to say 1s2, 2s2, 2p6. Just like that. And in case you're unsure, write magnesium out the entire way. Here's your 3s2. And now you have to say, well, what is magnesium going to want to do to become more stable? It wants 8 valence electrons, so it can either gain 6 here, or it can cut these 2 out, giving it these 6 now. And the last one, fluorine, with 1 excited electron. All right, here's fluorine. Fluorine normally has, let's see, 9 electrons, so it's going to be 1s2, 2s2, 2p5. So I'm going to choose one of those electrons and make it excited. Doesn't necessarily matter which one you pick, but you generally want to pick one of the outermost. It's more likely to become the one that's excited. So here's my 1s2, 2s2, 2p, up, 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 And now I would normally say down, down, and be done, but now I'm just going to say down, and then my last electron has to go somewhere. So you can put it anywhere you want. I'm just going to put it up one level in the 3s. So this is an excited state for fluorine. All right, last few ones here. Noble gas notation for titanium. Titanium is number 22. So the previous noble gas is argon. Bracket argon. And we continue with 4s2, 3d2. After that, aluminum. Previous noble gas before aluminum is neon. And we're going to tack on 3s2, 3p1. Ru is ruthenium, not rutherfordium. That comes later. Ru ruthenium, number 44. The noble gas before ruthenium is krypton. And we are going to add on 5s2. 2, 3, 4, 5, 6. 4d6. And finally, Cs, that's cesium. Uh-oh, I didn't go too far, did I? Oh, no, cesium's good. Cesium, and we're going to put xenon down, and then 6s. Okay, so that's it.